Module 7, Lecture B, Images, Custom. By the end of this lecture, you will be able to represent images as arrays and extract patch-based features, create graph structures for image neighborhoods and regular grids, and implement simple custom transformers compatible with Scikit-Learn pipelines. Image patch arrays. Image array basics. A digital image can be understood as a grid of numbers that record light at each pixel. In grayscale images, each number represents brightness, while color images add aligned red, green, and blue layers for every pixel. This view treats images as structured data, which is essential for extracting useful features. In image analysis, pixel arrangement matters because it preserves spatial relationships in the scene. Neighboring pixels can reveal meaningful patterns, such as sharp value changes that suggest edges or repeated values that indicate texture. Keeping both pixel values and their locations allows systems in areas like medical and satellite imaging to extract useful features from local pixel neighborhoods. Before extracting image patches, check that the image array is organized and scaled correctly. Its size defines the resolution, its channels describe the data stored at each pixel, and its numeric range affects how pixel values are compared. Because lighting and sensors can change brightness and value ranges, proper scaling helps ensure reliable feature extraction for machine learning. Python code, image array basics. This example represents an image as numerical pixel values. The positions of the pixels keep basic spatial relationships, and a small patch can reveal local structure in the image. We import NumPy to work efficiently with numerical arrays and mathematical operations, and Matplotlib PyPlot to create visualizations in Python. Together, these libraries provide the basic tools for handling data and displaying it clearly. We create a small synthetic grayscale image as a 6x6 array, where each value represents a pixel brightness. Lower values appear darker, while higher values appear lighter, producing clear contrast between regions. The image uses unsigned 8-bit integers, a common and efficient format for storing grayscale pixel values. The code first verifies that the image array is two-dimensional, confirming it is a grayscale image in the expected format. If not, it raises an error to stop processing. This check helps prevent later operations from failing because they rely on that specific image structure. Select a small 3x3 region of the image that includes a brightness change. Then, compute its average brightness. Converting the result to a floating point value gives a precise measure of the patch's local intensity. The code summarizes key properties of an image and a selected patch. It checks the image dimensions, reports the minimum and maximum pixel values to show the brightness range, and confirms the patch size. It then calculates the patch's average brightness and prints its pixel values as a one-dimensional list for closer inspection. Create a 5x5-inch plotting area with Matplotlib, then display the image on its axes in grayscale. Set the pixel range from 0 to 255 so the image uses the full black to white scale. To highlight a selected image patch, define the rectangle's corner coordinates so it surrounds the target area. Then, use Matplotlib's plotting function to draw a red outline with a thicker line and label it as a 3x3 patch. This makes the area of interest easy to identify in the image. The plot is finalized by adding a clear title, labeling the column and row axes, and including a legend to explain annotations such as the highlighted patch. The display function then renders the grayscale image with all labels and markings visible. This script builds a small synthetic grayscale image as a two-dimensional array with two brightness regions. It selects a 3x3 patch across a brightness change, computes the patch's average brightness and reports basic size and pixel range information. It then displays the image with the selected patch marked, showing how local image structure relates to the full image. Extracting image patches. Image patches are small rectangular regions taken from a larger image to capture local features such as edges, textures, shapes, or color changes. Each patch stores intensity information in grayscale images or color channel information in color images. Turning these patches into feature vectors gives machine learning models structured data for comparing patterns across images. When extracting image patches, the main choices are where to sample, how large each patch should be, and how far apart patches are placed. Dense sampling covers the image at regular intervals, while sparse sampling targets selected regions of interest. Smaller patches capture fine detail, larger patches add context, and the stride controls overlap, balancing detail against processing speed. After extracting image patches, you can flatten them for comparison or machine learning, or compute simple features such as brightness and texture. These local regions are useful for finding features or defects in tasks like agriculture, document analysis, and industrial inspection. Although patches increase the amount of data, they give models important local visual information to learn from. Python code. Extracting image patches. This example takes smaller image patches from a single synthetic image. Each patch is a separate image array, and the visualization indicates the sampled locations. We import NumPy for numerical work with arrays, Matplotlib's plotting tools for visualizing images, and Scikit-Learn's extract patches 2D function to pull smaller patches from a larger image. These tools support image visualization and feature extraction for machine learning tasks. A simple synthetic grayscale image is created as a 12 by 12 grid of black pixels. Two bright regions are then added, a medium bright vertical stripe and a fully bright horizontal stripe that crosses it. The result is a small test image with intersecting patterns, useful for basic image processing experiments. We define each image patch as 4 by 4 pixels, then use Scikit-Learn's extract patches 2D function to pull every possible patch of that size from the original image. The function slides a 4 by 4 window across the image and returns the resulting patches as an array. This makes the image easier to analyze in smaller sections. To verify patch extraction, we first compute how many overlapping 4 by 4 patches should come from the image, based on its rows and columns. We then compare this expected count with the actual patch array shape. If they do not match, an error is raised, helping confirm that the extraction logic is working correctly. Each image patch is flattened into a one-dimensional feature vector for machine learning use. We then measure the first patch's average brightness, rounded for readability, and compare the average brightness across all patches to find the index of the brightest one. This process summarizes key information about image patches for machine learning. It reports the original image size, the number and size of extracted patches, and the shape of the flattened feature matrix. It also measures the average brightness of the first patch and identifies which patch is brightest overall. Create a 5 by 5 inch plotting area with Matplotlib, then display the synthetic image in grayscale. Set the brightness range from 0 to 1 so the image contrast is shown clearly. The process loops through row and column positions that mark image patches, then draws an outlined rectangle for each one. Each rectangle is slightly offset to align with the image grid and sized to match the 4-unit patch. Adding these rectangles to the plot visually highlights the patch locations on the image. The plot is annotated to make the synthetic image easier to interpret. It adds a descriptive title, labels the horizontal axis as column index and the vertical axis as row index, then displays the image with the highlighted patch locations. This script shows how to use Scikit-Learn to extract all 4x4 patches from a synthetic 12x12 grayscale image. The patches are flattened into feature vectors for machine learning, then checked for expected size and basic brightness statistics. The output reports the image and patch dimensions, the feature matrix shape, the first patch's average brightness, and the brightest patch, while a plot highlights a few example patch locations on the original image. Rebuilding image patches. Rebuilding image patches means recombining small, separately processed image segments into a complete image. This is useful when tasks like analysis or classification are easier to perform locally, but the final result must match the full original image. For example, medical scans or satellite images may be processed in patches, then rebuilt into a full heat map or map for evaluation and machine learning workflows. When rebuilding an image from patches, overlap helps create smoother results and preserves details near patch edges. Because overlapping patches can estimate the same pixel differently, their values are averaged to reduce blocky artifacts. This is especially useful in denoising, where averaging makes the final image look more cohesive and less fragmented. When reconstructing an image from patches, the original image size, patch size, and extraction order must match exactly. If patches are placed incorrectly or the wrong shape is assumed, the rebuilt image can be distorted. This alignment is important in machine learning when comparing results with ground truth images or turning local patch scores into a full image, such as for locating defects in manufacturing inspections. Python code. Rebuilding image patches. Overlapping patches are combined to form one synthetic image. Averaging the shared regions smooths the reconstruction and restores common pixel locations consistently. We import NumPy for efficient numerical work with arrays and Matplotlib pyplot for creating plots and visualizations. We also import the extract patches 2D function from Scikit-Learn, which extracts overlapping image patches for tasks such as reconstruction or feature extraction. We create a simple synthetic grayscale image as a 6x6 array containing values from 0 to 35. This makes the image data easy to inspect and manipulate. We then choose 3x3 patches so the image can be broken into smaller sections for later reconstruction. We extract all overlapping 3x3 patches from the image using Scikit-Learn's extract patches 2D function. To check the result, we compute the expected patch count from the image dimensions by reducing both the row and column counts by 2 and multiplying them. This confirms that the overlapping patch extraction produced the correct number of patches. We verify that the number of extracted patches matches the expected count to confirm the image was divided correctly into overlapping patches. If the count is wrong, a value error is raised as a safeguard, indicating a likely issue with the dimensions or extraction settings. To rebuild the image from patches, we create two zero-filled arrays with the same shape as the original image. One stores the accumulated pixel values as patches are placed back, while the other counts how many times each pixel is updated. These counts allow overlapping patch values to be averaged correctly, and a patch counter is initialized to process the patches in order. The process scans every valid patch position in the image by moving across rows and columns. At each position, it adds the patch values into a rebuilt sum array and updates a count array to record how many patches contribute to each pixel. This handles overlapping patches, and the patch index advances after each patch is processed. Before rebuilding the image, we verify that every pixel received at least one patch contribution. If any pixel was missed, an error is raised. The final image is then formed by averaging the contributions at each pixel, which blends overlapping patches and produces a smooth reconstruction. We inspect the image reconstruction by checking the original image size, the number and size of extracted patches, and how many patches overlap at the center pixel. We then report the largest difference between the original and reconstructed images, rounded to 6 decimal places, to measure reconstruction accuracy. A square Matplotlib figure is created to display the reconstructed image. The image is shown in grayscale with nearest neighbor interpolation, so individual pixels remain sharp. The plot is given a clear title and axis labels for row and column position, then displayed to the user. This script shows how to rebuild a grayscale image from overlapping patches. It extracts all 3x3 patches from a small synthetic image, places each patch back in its original position, and averages overlapping pixel values to reconstruct the image. It also verifies that every pixel is covered and measures the reconstruction error, which should be very small, before displaying the rebuilt image. Image graphs. Pixel neighborhood graphs. A pixel neighborhood graph represents an image as connected pixels, helping show how information moves across the image. A 4-neighbor graph links pixels horizontally and vertically, while an 8-neighbor graph also includes diagonal links. This makes it easier to detect patterns such as roads in satellite images or edges in medical scans by focusing on relationships between nearby pixels. A pixel neighborhood graph represents an image by connecting nearby pixels according to the image grid. Interior pixels have more neighbors than edge pixels, reflecting the image's natural spatial limits. Connections may simply show adjacency or be weighted by similarity, such as brightness or color differences. This makes it easier to study regions, contours, and transitions than using raw pixel values alone. Pixel neighborhood graphs represent an image by linking each pixel to nearby pixels, making it easier to analyze visual structure. They help algorithms find connected regions, measure smoothness, and detect sharp boundaries. This supports tasks such as image segmentation, document analysis, and defect detection by showing how each pixel relates to its surroundings. Python code. Pixel neighborhood graphs. Create a small synthetic graph from a pixel neighborhood, then compare how 4-neighbor and 8-neighbor connections link nearby pixels. Finally, show the graph edges over the image grid to make the different connection patterns clear. We import NumPy to work efficiently with image pixel data, using arrays and mathematical operations. We also use Matplotlib's plotting tools to visualize the image grid and show how neighboring pixels are connected. We create a small synthetic image as a 2-dimensional array with 3 rows and 4 columns. Its integer values represent pixel intensities, stored as unsigned 8-bit data, which is common for images. Because the image is so small, each pixel can be inspected easily, making it useful for understanding pixel neighborhood graphs. The code first reads the image height and width to understand the pixel grid. It then checks that the image contains exactly 12 pixels, matching the expected 3x4 layout for the example. If the size is different, it raises an error to catch unexpected changes in the image dimensions. Each pixel in the image is assigned a unique node number by creating a sequence from 0 to the total number of pixels. This sequence is reshaped to match the image's height and width, so each pixel position maps directly to a node. This makes it easier to reference pixels when building a graph of their connections. Neighbor offsets define which nearby pixels are connected in the graph. 4 offsets create horizontal and vertical links, connecting each pixel to its right and bottom neighbors. 8 offsets add diagonal links, so pixels also connect to bottom right and bottom left neighbors. These choices control how the pixel graph is built. The buildEdges function creates undirected connections between pixel nodes using given neighbor offsets. It scans each pixel in the image grid, checks which offset-based neighbors stay within the image boundaries, and records a connection between the current pixel's node and each valid neighbor's node. The result is a list of edges that represents how neighboring pixels are connected. We build graph edges from image pixels using two neighborhood choices. The for-neighbor version connects each pixel to its immediate right and bottom neighbors when they exist, creating undirected edges. The 8-neighbor version adds diagonal connections as well, producing a more connected graph. Both edge sets are kept for later analysis and visualization. To measure brightness changes between neighboring pixels, we create a list of edge differences and examine each connected pair in the for-neighbor graph. For each pair, we get the 2-pixel brightness values using their linear positions in the image array, compute the absolute difference, and store it. These values quantify how strongly brightness changes across connected pixels. The output summarizes a small synthetic image as a graph. It first confirms the image size, 3 rows by 4 columns, and the total number of pixel nodes. It then compares how many edges are created using 4-neighbor connections versus 8-neighbor connections, where diagonals are included. Finally, it shows a few sample 4-neighbor edges and their brightness differences to illustrate how edge weights capture changes in pixel intensity. Create a new Matplotlib figure, an axis, with a 6x4-inch canvas. Then display the image on that axis using the image display function. Show it in grayscale and map pixel values from 0 to 100 so the brightness is represented correctly. This image becomes the background for adding the pixel graph. For each connected pair of 4-neighbor nodes, the code converts each node number into its row and column position using the divmod function with the image width. It does this for both the starting and ending pixels, then draws a cyan line between their positions with Matplotlib. This visually shows the connections between neighboring pixels on the image grid. The image is scanned row by row and column by column, so each pixel can be labeled with its node number from the flattened array. Each label is placed at the pixel's column and row position on the plot, centered and shown in yellow for easy identification. The plot is given a clear title and axis labels to explain the image grid, with columns on the x-axis and rows on the y-axis. The Matplotlib show function then displays the visualization, so the 4-neighbor pixel graph can be inspected on top of the synthetic image. This script builds a small pixel neighborhood graph from a 3x4 image, treating each pixel as a node. It compares 4-neighbor connections, which link pixels to their right and bottom neighbors, with 8-neighbor connections, which also include diagonals. It counts the edges in each model, measures brightness differences for 4-neighbor lengths, and visualizes the 4-neighbor graph with lines and node labels over the image grid. Regular grid graphs. A regular grid graph represents an image by treating each pixel as a node connected to nearby pixels. The simplest version connects each pixel to its 4 direct neighbors, while an expanded version also includes diagonal neighbors. This preserves the image's row and column structure and makes local relationships clear, showing how nearby pixels share visual information, such as color and texture. Regular grid graphs connect image pixels in a structured way, making them useful for graph-based image analysis. They help identify boundaries, spatial continuity, noise, and defects in areas such as medical imaging, satellite analysis, and manufacturing. Because their structure is predictable, they are well suited for segmentation and feature extraction. In a regular grid graph, edge strength defines how strongly neighboring pixels are connected. Simple graphs treat all neighbors equally, while weighted graphs make connections stronger between visually similar pixels and weaker across sharp contrasts. This helps algorithms use both image layout and appearance, such as linking pixels within the same clothing region more strongly than pixels across a boundary with a wall. Python code, regular grid graphs. Create a small, regular grid graph by treating pixels as nodes and connecting each pixel to its 4 immediate neighbors. Then show the resulting nodes, edges, and the degree of each node. The code begins by importing NumPy for efficient numerical work with arrays and Matplotlib's plotting tools for creating visualizations. Together, these libraries provide the basic tools needed to process data and display it graphically. We create a small synthetic image as a simple two-dimensional array with 3 rows and 4 columns. Each value represents a pixel intensity between 20 and 100, stored as an unsigned 8-bit integer, which is common for image data. This compact example makes it easy to build and visualize a grid graph. First, get the image height and width from its shape. Then check that both dimensions are at least 2. Otherwise, raise an error explaining that the image must be at least 2 by 2. This ensures the grid is large enough to create meaningful pixel connections. To build the graph, each pixel in the image is treated as a node. The process scans through every row and column, records each pixel's row and column position, and stores it in a list. This creates a unique graph node for every pixel, preparing the image for later graph operations. The process builds a list of connections between neighboring pixels in an image. It scans each pixel, and when possible, connects it to the pixel on its right and the pixel directly below it. By checking image boundaries first, it avoids invalid connections and creates a grid of edges across the image. Create a dictionary to store each node's degree, meaning the number of neighboring nodes it has. Then, go through the node list and set each node's degree to 0, preparing the graph so its connections can be counted later. To compute node degrees, go through each edge and increase the degree count for both nodes it connects. Since a node's degree is the number of edges attached to it, updating both endpoints ensures every connection is counted correctly. The code prints key checks for a graph built from a synthetic image. It reports the image dimensions, the total number of nodes, and the number of 4 neighbor edges between adjacent pixels. It also compares the degree of a corner pixel with an interior pixel, helping confirm that the graph's connectivity matches the image structure. Set up a Matplotlib plot with a figure and axis. Then display the image on the axis in grayscale. Using the upper left origin makes the plot match the image's pixel layout, so the pixel intensity values are shown visually. For each connected pair of nodes, collect their row positions and column positions, then use them to draw a line between the nodes with Matplotlib's plot function. Setting the line to blue with a moderate width makes the grid connections clearly visible. The code visualizes each pixel as a node by plotting a red dot at its grid position. It then adds a centered white label showing the node's degree or number of connections, so the graph clearly displays both node locations and connectivity. The plot is titled to identify it as a 4-neighbor regular grid graph. The axes are labeled by column and row index, with tick marks covering the image width and height, so pixel positions are easy to read. Finally, the plot is displayed for visual inspection. This script turns a small synthetic image into a regular grid graph, treating each pixel as a node. It connects neighboring pixels to the right and below, then computes each node's degree, or number of connections. The output reports the image size, graph size, and selected node degrees, while the visualization overlays nodes, edges, and degree labels on the image to show the graph structure clearly. Graph applications. Graph structures help image analysis by representing pixels as connected nodes, so algorithms can use both pixel values and spatial relationships. This makes it easier to group similar regions while keeping important boundaries, such as tissue edges in medical scans. The same idea supports satellite image analysis by separating features like roads and buildings, while reducing mistakes caused by noise. Image graphs help smooth and denoise images by controlling how information spreads between pixels or regions. They encourage similar values within the same object, while preserving real boundaries, making them more flexible than uniform filtering. This can reduce random noise in photos or inspection images without blurring important edges or defects. Graph representations help image processing by turning spatial patterns into features that machine learning systems can use. Grid graphs preserve the image layout, while adaptive graphs connect pixels or regions with similar color, texture, or depth. By making relationships between shapes and regions explicit, graphs support more robust and interpretable analysis in areas such as autonomous driving, agriculture, and cultural heritage. Custom transformers. Function-based transforms. Function-based transforms let you turn simple data transformation functions into standard steps in a Scikit-Learn pipeline. They are useful for image-derived features, such as scaling pixel values or computing summary statistics. Adding these transforms to a pipeline keeps pre-processing consistent and repeatable across training, validation, and future data. Function-based transformers are useful for fixed pre-processing steps that do not need to learn from data, such as resizing images, converting them to grayscale, or normalizing pixel values. They simply apply the same operation consistently within a Scikit-Learn pipeline, while preserving the required interface. This makes them easy to reuse across experiments and include in model selection without changing the overall workflow. Function-based transforms make feature extraction more structured by treating each step as a clear input-output operation. When these transforms fit into a pipeline, workflows become easier to reproduce, test, audit, and modify. This separation of feature extraction from modeling helps keep custom image analysis systems organized and maintainable. Python code, function-based transforms. Wrap image processing functions as pipeline transformers so they can work within a Scikit-Learn workflow. A function transformer gives these functions the standard Scikit-Learn interface, allowing the pipeline to output compact patch features. This setup imports the main tools needed to build and evaluate a simple machine learning workflow. NumPy supports numerical operations, while Scikit-Learn provides the digits dataset, pipeline tools, a function transformer, logistic regression, train test splitting, and accuracy scoring. Together, these imports prepare the code to load digit images, process the data, train a classifier, and measure how well it predicts the correct labels. We load Scikit-Learn's digit image dataset, which contains small handwritten digit images for quick experimentation. The images are converted to floating point values so their pixels are ready for processing, and the corresponding digit labels are extracted. This prepares the data for later transformations and model training. Before processing, the code validates that the image data has the expected format. It checks that the data is a batch of images, and that each image is 8 by 8 pixels. If the shape is incorrect, it raises an error, helping prevent problems later during feature extraction. This function normalizes a batch of images by dividing each pixel value by 16, scaling the values into a range from 0 to 1. This gives the model input data on a consistent scale, which can help machine learning algorithms train more effectively and converge more reliably. The patch means function summarizes each image in a batch by dividing it into 4 quadrants and computing the average pixel value in each one. It returns these 4 averages as a compact representation of the image. This reduces the amount of image data while keeping basic spatial information from the top left, top right, bottom left, and bottom right regions. A Scikit-Learn pipeline is used to process image data through 2 main transformations. First, a function transformer scales pixel values to the range from 0 to 1, with input validation skipped for efficiency. Then, Another function transformer computes the average pixel values for 4 image patches. Wrapping these steps as transformers lets the data move smoothly through the full feature pipeline. The dataset is split into training and testing sets, so the model can be evaluated on data it has not seen before. Using Scikit-Learn's train-test-split function, 25% of the data is reserved for testing. A fixed random state makes the split reproducible, and stratifying by labels keeps the class distribution consistent in both sets. We build a machine learning pipeline that first processes images with the existing feature extraction steps, then passes the resulting features to a logistic regression classifier. The classifier is configured with enough optimization iterations to help it converge, and a fixed random state for reproducible results. This lets the model train on transformed image features and make predictions efficiently. We train the full pipeline on the training images, allowing the logistic regression model to learn from the extracted features. The trained model then predicts labels for the test images, and its accuracy is measured by comparing those predictions with the true test labels. This shows how well the model performs on new, unseen data. A single image is passed through the feature pipeline, where scaling and patch mean operations convert it into feature values. These values are then rounded to 3 decimal places, making the extracted features easier to read and interpret. The output checks the Scikit-Learn version for reproducibility, then reports the image batch state before and after patch feature transformation. It also shows the first image's patch means, rounded for readability, and ends with the pipeline's test accuracy to summarize performance on unseen data. This script builds a simple digit image classifier using a custom feature pipeline. It scales each image, splits it into 4 patches, and uses the average pixel value of each patch as the feature set. These features are passed through a Scikit-Learn pipeline with logistic regression, trained on a training split and evaluated on a separate test split. The output includes the image shape information, the first image's transformed patch features, and the model's test accuracy. TransformerMixin Basics. TransformerMixin is a useful base for building custom transformations that work smoothly inside Scikit-Learn pipelines. It lets a transformer learn from training data and apply the same pre-processing to new data, such as image normalization or patch summarization. Keeping these steps inside the pipeline helps ensure consistent pre-processing, which is especially important in image processing where small differences can affect model reliability. Custom transformers in Scikit-Learn use fitting to learn or store information from training data, and transforming to apply changes to new data. Some transformers, such as image flattening, may not need to learn anything, while others, such as pixel normalization, do. TransformerMixin helps custom transformers behave like standard Scikit-Learn tools, making them work smoothly in pipelines where each step passes clean output to the next. Custom transformers should be simple, reusable, and careful to separate training data from future data. Any learned setting, such as a brightness normalization value, should be fit only on the training set, and then applied unchanged to validation, test, or new data to prevent leakage. Following the TransformerMixin style makes feature extraction easier to test, integrate, reproduce, and deploy, supporting cleaner software and more reliable machine learning. Python code. TransformerMixin Basics. This section builds a small custom image transformer for reusable pre-processing. The TransformerMixin provides standard fit and transform pipeline behavior, and the printed features confirm that the image pre-processing works as intended. We create a small synthetic grayscale image dataset using a 3-dimensional array. It contains 2 4x4 images, where each value represents pixel brightness as a floating point number. This simple setup provides a clear, self-contained example for demonstrating basic image processing. We create a small synthetic grayscale image dataset with NumPy using a 3-dimensional array. It contains 2 images, each 4 pixels high and 4 pixels wide, with each value representing a pixel. Using floating point values makes the example flexible and self-contained, so image processing techniques can be tested without external files. The code verifies that the image data has 3 dimensions: samples, height, and width. If the shape is not correct, it raises an error to stop processing. This check ensures the data is properly structured before it is used. The brightness centerer class adjusts image brightness and is built to work with Scikit-Learn pipelines. It uses standard estimator and transformer behavior, so it can fit data and then transform it. During fitting, it calculates the average brightness of the training images and stores that value for later use, then returns itself to support pipeline chaining. In the transform method, each image's brightness is adjusted by subtracting the mean brightness learned during fitting. This centers brightness values around 0, helping normalize the images, so brightness differences do not interfere with later feature extraction. The patch mean features class transforms images by computing the average brightness of selected image patches. It is built to work smoothly in Scikit-Learn pipelines by inheriting standard estimator and transformer behavior. Its fit method does not learn from the data. It simply returns the transformer itself, so the later transformation step can be applied. The transform method summarizes each image by dividing it into 4 quadrants and calculating the average value in each one. It computes the mean for the top left, top right, bottom left, and bottom right patches, then combines these 4 values into a compact feature representation. This reduces each image to 4 meaningful patch averages for later analysis. A Scikit-Learn pipeline is used to apply image pre-processing steps in a fixed order. It first centers each image's brightness using the mean brightness learned from the training data. Then it divides each image into 4 patches and computes the average brightness of each patch. This keeps the workflow organized and ensures the transformations are applied consistently. The pipeline uses the fit transform method to learn from the image data and transform it in one step. It applies brightness centering and patch mean processing, producing a feature matrix where each image is described by its patch mean values. The resulting features are then rounded to 2 decimal places to make them easier to read and interpret. The output summarizes key checks from the image processing pipeline. It reports the input batch shape, the learned average brightness from the training data, and the shape of the transformed feature matrix. It also shows the patch mean features for each image, which give a compact representation by averaging different image regions. This script shows a simple Scikit-Learn image processing pipeline for batches of grayscale images. It first verifies that each input has samples, height, and width, then centers brightness by subtracting the average brightness learned from the training images. Next, it splits each image into 4 quadrants and uses the mean brightness of each quadrant as features. The output reports the input shape, learned mean brightness, feature matrix shape, and rounded patch mean features for each image. Feature name handling. Custom transformers should preserve clear feature names, so transformed columns remain meaningful in a machine learning pipeline. This is especially important when original measurements, such as image-based features, are converted into new inputs. Clear names make the results easier to interpret, explain, and trace back to real-world context, which matters for teams evaluating models beyond predictive accuracy. Custom transformers in Scikit-Learn should work smoothly within larger pipelines and produce consistent, meaningful feature names. Unchanged features should keep their original names, while new features should have clear names that describe what they represent. Stable and readable feature names make pipeline outputs easier to inspect and understand. Clear and consistent feature names are important for reproducible machine learning pipelines and effective teamwork. They help data scientists, domain experts, and engineers understand, review, and deploy transformed data reliably. Even when a transformer changes its output based on the input shape, it should provide meaningful names so the results remain interpretable and dependable. Python code, feature name handling. Build a transformer that keeps feature names readable and meaningful after transformation. This confirms that the output uses names compatible with a pipeline. We import key tools for building a data transformation pipeline: NumPy and Pandas for numerical data and data frames, and Scikit-Learn components for custom transformers, pipelines, and feature scaling. The base estimator and TransformerMixin help custom steps work smoothly with Scikit-Learn, while the pipeline chains processing steps together. The StandardScaler prepares features by centering them and scaling them to unit variance. A small Pandas data table is created to organize image-based measurements for analysis. Each row represents an image or observation, and the columns store average red intensity, edge density, and patch brightness. This structure makes the image features easy to manage and use in later processing. The brightness ratio adder class is a custom Scikit-Learn transformer built by inheriting from the standard estimator and TransformerMixin classes, so it can work inside a pipeline. Its fit method accepts the input data and an optional target, then stores the input column names as feature names. This helps preserve feature name consistency after transformation, and returning the transformer itself supports normal pipeline chaining. The transform method first converts the input into a floating point array and checks that its columns match the features saved during fitting. It then finds the average red and patch brightness columns, computes patch brightness divided by average red while avoiding division by 0, and adds this ratio as a new feature to the dataset. This method creates clear feature names for transformed data. It takes the existing feature names, adds a new name for the brightness to average red ratio, and returns the full set as a NumPy array. This helps keep machine learning pipeline outputs interpretable. A pipeline organizes data processing into repeatable steps. Here, it first adds a new brightness ratio feature with a custom transformer, then standardizes the data with a StandardScaler by centering features and scaling them to unit variance. This keeps transformations consistent and easy to apply. The pipeline transforms the image feature data by adding a new feature that compares patch brightness with average red, then standardizes all features to a common scale. It also retrieves the updated feature names so the new feature is included. The transform data is then placed into a new table with those column names and rounded values for easier reading. The output first checks the Scikit-Learn version to support reproducibility, then compares the original image feature names with the transformed feature names after the pipeline adds a new feature. It also reports the transformed data shape to show the resulting dimensionality. Finally, it previews the first 3 transformed rows, rounded to 2 decimal places, so you can quickly inspect the pipeline's results. This script shows how to use a custom transformer in a Scikit-Learn pipeline while keeping feature names meaningful. It starts with image features such as average red, edge density, and patch brightness, then adds a new brightness to red ratio feature. The pipeline scales the resulting features and prints the original and transformed feature names, the data shape, and a small preview. The main point is that custom transformations can add useful features without losing clear feature labels. In this lecture, you learn to represent images as arrays and extract patch-based features, create graph structures for image neighborhoods and regular grids, and implement simple custom transformers compatible with Scikit-Learn pipelines. In the next module, Module 8, we will go over kernels approximation.
Thank you for your attention. See you all in the next lecture.